Okay, so this is a problem number 3. It's once again the problem about isomers, and they are showing you this complex PtCl2 NH3 2+. Right? So let's, before actually going to chiral isomers, isomers, I'll talk about this. So this means a chloro, there are 2 of them, and so this means make it 2 minus charges there. And this one is neutral, right? No charges. This one is -2. So the overall is a neutral, so that makes a platinum 2+. Right? So then you can do this, the nomenclature. Let's do the nomenclature on the other side. You say, okay, platinum. Platinum is 2+, and then you can say dichloro, and what was an N? NH3. NH3. Remember, NH3 is ammonia. It's just called AMMINE. Okay. So this is a diamine. Okay, so those are the compounds, and then which one comes first based on the alphabetical rule, which doesn't count the di, but the one that matters is the one coming after the numeric portion, right? After the numeric portion, which is a C versus A, so A goes for first. So therefore, the nomenclature is diamine, dichloro, platinum 2. So that was a nomenclature. So that's another exercise for you. But now what you can see to develop your eyes, as they said, it has 2 distinct forms. So what you can see from looking at here, platinum has 2 chlorines and NH3 2 to ammonia, right? Ammonia is attached to it. So almost like a platinum, in a very naive way, there are 4. Right? Chlorine, NH3, NH3. Okay, so it has lone pairs. There are lone pairs. I'm pretty sure lone pairs. And but when I draw it, so they're going to say, they actually told me that this complex is tetrahedral or square planar. And the fact is, this compound can be obtained in 2 distinct isomeric forms. Okay, so this is 2 isomeric forms. So what you can do is, okay, so first, if tetrahedral, okay, TD is a tetrahedral, that means you can put platinum in the center. You can put things like this, NH3, and the Cl minus and Cl minus. Okay, Cl minus, that's a 2+. That's what's going on inside. And so this is a tetrahedral. I put a very weak colors. It's almost like this. So this is a tetrahedral structures, and if you remember actually from the tetrahedral, just a carbon, 4 attachment have to be all different. Okay? And as you can see, but these attachments are the same. So this one cannot have the optical isomers. So that's the one way to look at that tetrahedral as you form learn from the carbon, right? Carbon in chemistry 1, and we talked about tetrahedral optical isomeric center, and you need to have all of them. And I remember talking about alpha, beta, gamma, delta. They have to be all different for the tetrahedral. So that's the one way. Another way for you to look at it is, okay, PT with, that's how I draw. So that's NH3, Cl and Cl. And then let's do the mirror complex. So, okay, so then if I do this, PT with NH3, Cl and Cl, and then these are, you will find out that's a superimposable. Okay, so superimposable means these are not chiral isomers, but chiral isomers. So what that means is are the same, they are the same. If it is a superimposable. Okay, so therefore tetrahedral cannot be the answer. Okay, and so number 2 is another possibility. They said, well, okay, so what about if square planar? So in that case, the picture is pretty simple. What I need to do is I'm going to put a square planar, and then I'm going to put platinum, and then I can put chlorine here, NH3, NH3. Okay, so these are so in a way, I think I should put it the other way around. So it's more like this, and that, and they form the square planars. But what do you see here? This one, if you put once more, this is a mirror, and you will find out the one that is NH3, PT, NH3, Cl, and Cl. They are superimposable. Okay. So okay. So they are not forming some I guess chiral isomers. So this is not chiral. So this is not chiral, non-chiral, and that's the only arrangement. But this one, what we call, although it is a non-chiral, we can say the first one is, we can say that's the same side, so this is a cis isomer. And then the second one that you can think about is putting a square, and then the platinum in the middle, and it's going to be opposite side, and then the NH3 goes to the other side. And this is what we call the trans isomers. And so they can form this cis and trans isomers, although they cannot non-chiral isomers. Okay, they are non-chiral, but depending on the location, they are on the same side, or they can be on the opposite side. And so these are the ones that can form these isomers. Okay, so they can form cis and trans isomers. And when you go back to this here, they are not only achiral. If you put this one onto the different locations, and such as if you put a platinum, and then if you put chlorine here, and if you say, okay, how about putting a chlorine this side, and then NH3, this is the same. Okay, because of the special connectivity they can tumble this molecule around. So there is even no cis trans isomers either. Okay, no chiral. That's for sure. But even that. So the answer for is distinct isomeric forms of cis and trans. We call that this is a geometric isomers, and this is a geometric cis and trans isomers. So geometric isomers. Okay, so that's possible.